As I said, I told you that we were talking about self-driven systems, and I decided directly to talk about a coarse-grained approach. And what that means, I didn't do very much about how a single particle propels itself, or I give you some examples, but I went straight into coarse-grained systems, and I went straight into ordered phases. Okay? And I showed you the Toner 2 model. So again, historically, people wrote down computer particle models with some simple rules. I went directly into a continuum theory, and I motivated that by saying, which was like, a vector, classical spins, kind of xy if you're thinking in 2 dimensions, but so which were also velocities, right? So I wrote down this model where I said that, look, you've got these spins and s dot. I'm trying to stick to my notation of last time, but tell me if I'm making a mistake. I think I used arrows on the top and now I'm putting lines below. That may be one mistake, one difference. Okay. So this was just plain XY dynamics. And then I added a couple of things. I said that I don't know what the coefficient was here last time, but let me use this. I introduced a density, and I said these guys can reorient in the presence of a density. And then crucially, I said that they can advect themselves. So this part, and noise. I'll say a little bit about the noise today, much more about the noise. This part was just the kinds of dynamics that Uwe wrote down for various spin models. It's also the dynamical version of what John Cardy talked about today in the XY model, right? That was this part of the dynamics. And it's very important, that aspect, because the kinds of large fluctuations in the angle, etc., that came up in what John was saying will come up again today. But interestingly, and old Marxists will understand what this means, it contains the seeds of its own destruction. In this particular context, because of this piece. We'll try to see that today. And then I said that, well, there's a density, and because this S is like a velocity, right? This was the model that we worked with and derived some consequences of last time. Although I made a big fuss about this being a non-equilibrium statistical mechanics problem, really all I did last time was to derive some kinds of average properties. But that's a perfectly respectable enterprise because, as I said last time, one of the purposes of microscopic statistical mechanics is to derive the macroscopic average properties of matter. Thermodynamics, hydrodynamics, elasticity, that kind of thing. So what we've done is at that level. However, the fact that we introduce these weird terms, I will explain today, comes in directly from the fact that you're breaking detail balance, and I'll show you in some way, okay? So last time what we managed to do was to study the ordered phase, and we consider an ordered phase where everybody is pointing this way on the average, that's the x direction, and we looked at fluctuations. Remember, the ordered phase comes in when this coefficient A is less than 0 within a mean field description, so that the state S equals 0 is unstable to the spontaneous formation of S. And then we looked at disturbances in that ordered phase, and we noted that if you say that this is S0, and this is the actual S, and this is delta S, then delta S y is of order theta, and delta S x is of order theta squared. so we won't worry about delta Sx in a linear theory, right? And then what we were able to show was that within and we did this by co-moving with the flock in a certain sense. We sort of said, yeah, I know that an aligned state is something that's moving, and actually, strictly speaking, that aligned state disturbances on average are not moving at the same speed as the flock. But let's not worry about all that. We sort of shifted frames, and we got this nice picture where rho dot is dy delta theta, theta dot, don't need a delta here really. Rho dot is dy theta, and theta dot is dy delta rho, and we got propagating modes, right? So this was the average dynamics. As an exercise, I would like you to work out dispersion relation, that is the relation between frequency and wave number, without making all these simplifying assumptions, so-called in the lab frame. Please do this and we can discuss this in the tutorial tomorrow. Okay? Right? Yes. Everything I'm going to talk about is entirely classical. So these are just... Yeah, but you know, rho, delta rho, the mean state, and yeah, let's call it that. You're absolutely right. Yeah. Yes. Yeah. Yes. So the reason that we don't have to assume that is that the way a state with non-zero velocity appears is because of this term. This term, so let's actually remember I talked about a toy model of self-propulsion. This part of the dynamics, if you think of S as a velocity, if you just look at the local, forget the gradients, S dot equals polynomial in S. That piece, if A is less than 0, amounts to S relaxing in a potential that for A less than 0 looks like this. And therefore, the magnitude of S can vary, but the relaxation rate of the magnitude of S remains non-zero even when wave number goes to 0, because it has to, if you globally change the length of the spins, there's a restoring force for that. Therefore, on time, and that means in a finite amount of time, exponentially speaking, there'll be a relaxation which will make the variations in the magnitude go away. Second exercise. Yes. You're right. Yeah, absolutely, because, you know, theta squared is also kind of slow. So there is that subtlety. Yeah, but it's subdominant. Yeah, I know, you know, truth is not only stranger than fiction, fiction is often easier than truth. Okay, so, yeah. Okay, so I lied. Okay, so it's, yes. Yes. Yeah, but you know, again, of course, it varies here because of the fluctuations. What I'm saying is a long wavelength theory need not worry about that. And that's actually true of real flocks also. Achha, by the way, I had forgotten to give you guys references to the literature. Sometime today I sent the organizers a few review articles. They're my favorite review articles for a reason which will become very obvious if you look at them. But on the particular topic of flocks, of real bird flocks, there is a very nice review which I did not send you, and which I think is not cited in those because it came out later. It is by, where do I write it? So it's by Cavagna and Giardina. It's in Annual Review of Condensed Matter Physics. A couple of years ago, I don't remember, you can check. What is very important about this work is that it's called flux as condensed matter or something. And the point is, these guys take this approach to describing bird flocks seriously enough that, like good condensed matter physicists, they measure correlation functions of bird flocks. How do they do it? They have movies mounted on the top of Rome's main railway station, video cameras mounted on the top of Rome's main railway station, and they take lots and lots and lots of pictures and analyze them very seriously. It's a spectacular piece of work. It's a real, it's a tour de force of modern technology also, the way they do all this. And that's the way to approach this subject. You finally have to confront experiments against theory. And one of the lessons of their findings is that these models are inadequate. They're inadequate in a much more serious way than any of the questions that were raised today might suggest, because it looks as though the interactions are not local in space, they're local in who's my nearest neighbor. It doesn't matter how far away the nearest neighbor is. In other words, each bird looks around and aligns not with its friend within 1 meter, but it's the first half a dozen people in its line of sight. If you dilate that whole region, the interaction does not weaken. That means it's not like a compressible magnet. Okay, that makes a big difference. You can start from a microscopic theory and build these kinds of theories. Some of the features survive, some are different. And that's not an irrelevant perturbation, that's a relevant perturbation in the technical sense. Okay, so I'm getting, as usual, yes sir. There's a literature, there's a lot, the whole synchronization literature does these approaches. So many things change. Clearly, the notion of propagating waves no longer makes any sense. You have one big megaspin in some sense doing something. Then it'll depend a lot on, meaning that what you can do is, see, there are people who live in real space and there are people who live on networks. Typically, physics department people live in real space, complex systems people live on networks. Physics department people live in space where there's a conventional distance. Complex systems people live on a space where distance is defined by what they call an adjacency matrix. D by dt of the ith guy is jij times the value of the other guys, the jth guys, where jij matrix could be completely non-local in space. And it's good for some purposes. So we won't do that, but yeah. Like where SID works now is a place where people do that kind of thing. Adjacency matrices, networks, all that. Yeah. Okay, so you can read more about this here. Second homework problem I wanted to give you. Again, let me rub this out and I'll give you the other homework problem. I've forgotten what it is now. Yeah, I know. So keep track of, so let S, so this is theta basically. So in other words, include the magnet. I've said the longitudinal bit, but equally you could do it to the magnitude. Okay. Keep track of the variations in S along its length. What you will find is that they relax in a finite with a finite decay time, and you can eliminate them to get an effective dynamics, which will still be what I said. But do the whole thing. It's algebraically only mildly painful. If you like, first do it without all this stuff. First do it just for XY. Forget about the density. And at least then you'll understand, I mean, that's, in the context of superconductor, that's the amplitude mode. It has mass equal to twice the curvature in the disordered phase. All that stuff you can work out. Yeah, okay. So what I want to do today, before I get completely distracted, is that, really I've just been doing mechanics, as I said. Let's do some stat mech. And in this context, stat mech means putting in the noise. In this very simplified description, this equation should be treated as an identity because we're treating S as the velocity field of the particles. Okay, so I don't need to introduce a diffusion and a noise here. I can do that, it'll change things in uninteresting ways for the most part. What I want to do is to deal with this noise. Okay, so the noise, I'll assume it's as simple as possible. Remember, the velocity, motile organisms move through a medium. That's why this object, if regarded as a velocity, can get damped out even at zero wave number. That is, a uniformly, supposing you've got a bunch of objects lying on that table and I set it in motion, friction will bring it to rest. Okay? Therefore, I have, the means, but then they're also propelled and therefore, some combination of friction and propulsion and saturation leads them to have a fixed speed. So the noise, therefore, if I think of a bunch of objects moving through a medium, each object can slow down or speed up without necessarily affecting the velocity of other objects. There's no overall constraint that all the momenta have to add up to a constant. Right? Therefore, the noise is non-conserving. And I think Uwe would have talked about both kinds of noises, right? Because you talked about model, for example, remember when we talked about model A and model B? In model B, the total order parameter, the integral over all space, the order parameter was a constant. And that had to be true not only on average, but even in the fluctuations. It's a strict constraint. We don't have that here. We have a non-conserving noise. If I put a noise into the density equation and a corresponding diffusion, that noise would have to be conserving, assuming these birds aren't being born and dying. All right. So what we'd like to do is just a little bit of algebra. And I actually won't do the algebra in any detail. Let's first let's just do the XY model. So I forget there is no rho, and so this coefficient lambda is 0, and forget the density. So then what you have is, if you write S as being S0 cosine theta sine theta, then as part of the assignment I gave you, you will have shown that the effective dynamics of theta is plus a noise, and this noise will basically be, I can write this on. This is a scalar unit strength white noise. And it's white, it's a function of x and t, and it's white in space and time. Spatial and temporal correlation is delta. Okay? And again, as John Cardy was saying today, we're forgetting here that this angle is an angle. There's nothing, the equation won't change. What will change if I remember the equation, the theta is an angle, is I'll write theta is an angle. Okay, so for this problem, you can work out very easily that the theta the difference between this and what John calculated was those were at equal time. There was no dynamics in what he did. We're now doing this in time. This will be the integral times something which I'll call C of Q and omega. And this is just a definition. I'm just using the fact that it's translation invariant in space and time to write it this way. And then we can calculate CFQ omega from these equations by Fourier transforming in space and time. And what we will find is that CFQ and omega is this, of course, is part of, it's not an additional exercise, this is part of the exercise you already have. Well, no, maybe. I only asked you to calculate dispersion relations. This is an additional exercise. I'll sketch how it's done. Right? For each, supposing you Fourier transform in space, that becomes a minus q squared. And this is a linear equation, so all the Fourier modes are independent. Each Fourier mode is just a single relaxing variable. It's like a harmonic oscillator with no mass and only damping. It's like an RC circuit with noise. Right? And that variable relaxes. And these guys are coupled in space, but in Fourier space, these guys are independent, and the noise will be a spatially uncorrelated noise in Q space. And so this is just saying that the system relaxes exponentially with a relaxation time 1 over kq squared. And this noise trend. So this is straightforward. Please do this. Please work it out. Okay? The reason this is important is it tells you what John already told us earlier today, which is that well, remember John calculated an object which he, I don't remember the notation exactly that he used, but basically, if you take this guy, he calculated this today, and he wrote it as an integral dq, actually in our case d2q, 1 minus, it's probably a half somewhere. I think I've got everything, right? Times, oh, I've already got this, sorry. Times S, a thing that I'm calling SQ. And this SQ with this notation. Okay? And it's also equal to what you get by integrating this guy over omega. Okay? So what John told you is that these differences between angle values at different positions grow logarithmically with distance, which is a consequence of the fact that in Fourier space, and that's in 2 dimensions, is a consequence of the fact that in Fourier space, this variance diverges of 1 over q squared. Okay? This is happening ultimately because the system condensed into a state which we called the x direction, but the system doesn't know the alphabet. It could be any direction. And it could have equally well condensed into any of those. As a result, very long wavelength variations in the angle stick around for a long time, are easy to produce and stick around for a long time. Right? This is all just XY model physics. The point about this is the effect it has on the angle variable. So we can do a lot more algebra. We can include the density. Okay. And what we will find when we include the density is, so this is just for plane XY. This is B. Include the density. So then this is linearized 1 or 2. And then I have to look up just to be consistent with my notation. Something like q perp squared over looks awful, and there'll be some coefficient. I won't stake my life on this coefficient. We'll have to check this. I'm reasonably sure this is right, but presumably something else happens when I forgot to introduce notation. I'd called something y, and now I'm calling it perp. So in general, I'll also call this direction parallel, and that all the other directions perp. In this two-dimensional case, that's one parallel and one perp, but I'll call all of them perp. Okay. I'm mildly worried about whether I only have this. This is the dominant version, but if you go to wave numbers, if you go to q perp equals 0, there'll be something else. Okay, so check this. What does this thing look like as a function of frequency? As a function of frequency, it'll have a peak here and another peak here, and these widths are of order kq squared. Kq squared, I guess. Right? Like sound waves. But there is a difference, and what is that difference? That difference is that as you go to smaller and smaller q, this comes down. I'm reasonably sure this is right. Let me make sure it's actually right. Yeah. You can check. I take it back. Sorry. I've skipped a step. This is not, I'm sorry. Please correct your notes. What I'm calculating here is not the angle correlation. What I'm calculating here is the density correlation. I should call it something else. So what have I done? I've gone here. I've used this equation to note that for small fluctuations, remember, and if I co-move, then this is approximately rho 0, S0 del y theta, right? So rho dot and rho and theta are related. I can calculate the density correlator from the angle correlator. So this is actually a very strange relation, because supposing instead of a flock, you just had a liquid crystal where everybody had lined up in some direction. That orientation is an orientation, but it's not a velocity. So if you have a long wavelength variation in that orientation, that doesn't give rise to huge changes in the density. So you should look at before I go into the algebra of this bit, let me just draw a cartoon here. So what kind of disturbances are we talking about? We're talking about, especially we're talking about disturbances wave vector along y, we're talking about this kind of thing. Right? So I'm talking about a variation in the orientation as you go in the y direction. Supposing this is the picture at one instant of time. So let's say this is at time t. At time t plus delta t, this region will be low in density, this region will be higher in density, this region will be higher in density, this region will be low in density, and so forth. So and these orientational fluctuations at long wavelength are easy to excite. But because they are not just orientations, but they are velocities, the result is that they produce density fluctuations that are as big as the orientational fluctuations. Remember, these excitations travel in a wave-like manner. Therefore, an omega, a d by dt and a d by dy are the same kind of thing. Therefore, the variance of density fluctuations at small wave number is as big qualitatively as the variance of orientational fluctuations. In any system which is spontaneously broken a continuous invariance, normally transverse fluctuations in the order parameter are big. That is why the angle variable has this property. This, which is a consequence of the order parameter being a velocity, means the density fluctuations are every bit as big as the angle fluctuations. Okay, and that's a huge effect, right? That's completely different. That's different from the XY model. That's different from a compressible magnet. That's different from Navier-Stokes. That's a property of an active system. That orientation implies velocity, and therefore orientation fluctuations imply current fluctuations. Okay. Yes. in a shady way. I said include row. You have to do as a lot more algebra, but it will add algebra beyond a point. Sort of obeys the law of diminishing returns. So I won't do it. It means I'm lazy. So you can do that. I mean, it doesn't change the story seriously. This is qualitatively correct. I won't stake my life on every coefficient. Okay, this form is right. And the important thing is, you can now take this object and integrate it over frequency to give you the static structure factor, the spatial Fourier transform of the spatial correlation function of density fluctuations, right? And if you do that, you can very easily guess what it will be. You can do an integral by looking at it and intimidating it. The denominator is approximately estimated by setting this term to 0 because the dominant contribution comes from here, right? So that's gone. So you have this, and there is a width, and that width is kq squared, okay? And this omega you replace by a q perp squared. Okay, so that and that goes as 1 over q squared. If you did the same calculation for an ordinary equilibrium compressible fluid, you'll get sound peaks, but the weights will be different. You have an extra factor of wave number squared upstairs. As a result, when you do the integral, you'll get a quantity of order 1. Why is the static structure factor for a fluid, why does it have a value that's neither infinite nor 0 at 0 wave number? Because a fluid has a well-defined compressibility at 0 wave number. This system, so that has to match that thermodynamic fact. This system is totally different. And you can do these integrals and you get this. So you now have the first non-trivial fluctuation fact about an active system. That is, the density in general is prone to very, very big fluctuations. Okay? So what's going on here? Basically what's going on is that it's a kind of merger of a general fact about systems with spontaneously broken continuous symmetry and the consequences of that in active systems where the continuous symmetry is associated with the direction of motion. Okay? And so these large fluctuations, which are, I guess, you can call them the Nambu-Goldstone mode of flocking, of the XY model in this case, but flocking also, invade the density field, which doesn't happen in magnets, it doesn't happen in equilibrium liquid crystals, it happens in these systems. So, of course, this answer is wrong in detail. In other words, if you do a real theory rather than a linearized theory, this changes. Okay? And calculating that is something we may or may not be able to do in these lectures. I will give you an idea of how those kinds of calculations are done. But I've said linearized tornado. Okay, so that's one cool fact. I had a well-defined plan of action, and I'm going to try to stick to it. Yeah. The next amazing fluctuation fact is the following. This, John Cardy told you today, means that the ordered phase isn't an ordered phase. What does that mean? What it means is, I can axe this. No, This? That? Oh yeah, there's a big board, yeah, so I can go there. Yeah. So, the fact that the angle fluctuations have this behavior, which means that this guy is proportional to the noise strength over K into something like the log of the system size over some microscopic size. This is what John told you today. Means that remember, what's long-range order? Long-range order doesn't mean the system picks some orientation and sticks with it. Really, the true meaning of long-range order is that you have a big system. If you prepare everything pointing like this at this end, and then you measure the probability that it's pointing the same way as a function of distance, then infinitely far away, that probability goes to a non-zero value. So if you prepare everybody at that wall pointing that way, and you measure further and further away, you have long-range order if in the limit of infinite distance there is a probability greater than zero that those guys are pointing that way. Okay? That's not what happens in the XY model. Minus some power, let's call it eta. Okay? And you can calculate that power. Basically, this is, e to the I, this is average e to the I theta of r minus theta of 0. Or the real part of it doesn't really matter. And that, as John told you, is e to the minus a half which ends up being e to the minus a half, all those constants times log L over A, which goes as L over A to some negative power. That power is non-universal, it depends on all the constants here. And it's, you can do this. Again, if John didn't assign it to you as an exercise, I'm assigning it. Do it. This is for the XY. It turns out, and is what Tamas Vicek found when he simulated his microscopic model for the same thing, which I haven't told you about in any detail, but you must have read about. Computer experiments. So this is okay for the XY model. But not for the flock. So one of the questions is, why the hell? Clearly the answer must have to do with the fact that this isn't the XY model. You might wonder if coupling to the density saves your skin. No, it doesn't. At a linearized level, you can check that because you're going to. Okay? Nothing nonlinear in the densities. Well, actually, no. It's more complicated. The case where we understand it perfectly is in the case where we throw away the density. And I'll come to that in a second. Okay? So the model is clearly more complicated than the XY model. It's complicated in many ways. It's complicated not only through the terms that I've written on the board, namely this and all this stuff. It's also complicated because if you build a continuum theory like this from the microscopic model that Mr. Vicek studied, which was, what is that model? Basically, you've got things that point in some direction and they look at their neighbors and they try to line up parallel to their neighbors and then everybody moves in the direction in which they're currently pointing. Try this at home, on your computer. Okay, and you will find that if there are two control parameters, one is the noise, which is how accurately these things estimate their neighbors' alignment, what error they make. The other is the density, the mean number of neighbors in a neighborhood of fixed size. What you find is what Vicek found. Actually, what Vicek found was this. Let's say that's density. That's noise. I always get this wrong, so you have to large density and low noise. So down here, yeah. So I think he found something like this. Long range order. Not this, but the truth of the matter is even more complicated. It turns out that actually, if you do much more careful numerical studies, there are two transitions. There's disorder, there's bands, and there's conventional flock. I don't know if we'll have time to get into this. Okay, you read about it. And this is due to studies by Chate and group. Okay, but the point is this, what we are concerned about is this. How do we understand this? So, if you start from the VIII model and build that kind of PDE, what you find is indeed this kind of PDE, but with density dependencies all over the place. Naturally, because there's no reason for them not to be density dependent. Whenever you build a coarse grain, when you build the Navier-Stokes equations from kinetic theory, every single phenomenological, every material parameter that depends on density and temperature. Okay? So, every damn thing here will and so forth. So it's a pain to deal with that. More than that, it's not even a simple grad rho. It's, one coefficient times grad parallel rho with another coefficient times grad perp rho. And not only rho, but there are other terms of this sort and so forth. So, and grad parallel and grad perpendicular are with respect to S, and that means these are awful nonlinear terms. Grad perp means 1 minus S hat times grad, right? So it's a term coupling S. So it's a mess. We won't go there. What we will do is the following. We will say that we'll allow these guys to be born and die. Okay, so let's say they're born. Imagine they're being spontaneously generated at some rate k plus, and if they're there, they die at some rate k minus. Okay, so then you can see all of a sudden the density, which was a slow variable, has now become a fast variable. So if you take this equation and ask for what happens to the total density, total number, the macroscopic density, it has a relaxation rate k minus. So on time scales long compared to k minus, we can forget the density. Totally, yeah. So what it means is that this makes the density fast. Remember, right? This is life in the slow lane. We're totally uninterested in fast variables. Right? Remember, we said the only things we care about are things whose relaxation time goes to infinity as the wavelength you're looking at goes to infinity. These guys have got this is like massive, supposing you were studying, suppose you want to understand long-range forces in nature, you do not care about massive particles. Right? So it's just like that. You only care about the slowly decaying stuff. And so we're in business, okay? We can, of course, take this equation, include other terms in S, and see, what this equation actually tells you is that the density on the density doesn't go to zero. I'm saying that density fluctuations relax to zero, right? You can just, the balance between these two terms determines the mean density and fluctuations. So basically what you will find, if you go to zero wave number, where rho zero is just, got it right? K plus or K minus, right? Yes, and d over dt of delta rho doesn't know about K plus, it only cares about K minus, plus order ingredient. But if we go to small wave numbers, we forget about this. So we forget delta rho. So you can set rho to a constant everywhere here. That means these terms are all unimportant. I abolish the density. Yeah, there's some background, of course, you've got to have some birds there, otherwise nothing will happen, right? So then we forget these guys, right? And we forget every single density dependence here, in case we ever worried about it. So this was Toner 2012. I really want to tell you about stuff that I've done, but I'm afraid I'm being a little historical about this. So now we have a model which is beginning to look a little bit more tractable. in fact, what I'm going to tell you is not in the next. What's my time like? We'll discuss this model next time. What I'll tell you just now is, I don't mean proved in a mathematical sense, but this is the model in which long-range order was established beyond any doubt. The original Toner 2 paper did an approximate calculation to argue for long-range order, even with the density. The status of that is that some things were ignored and so forth. So it's not watertight. This is watertight. I will tell you about this after I teach you how to do functional integrals for field theories next lecture. Today's lecture, I'll give you a heuristic argument, which is actually more beautiful, differently beautiful from the full. There are particles. These are moving. The density is the density of the occupancy variable of the particles. No, but that won't. I mean, you have to then put in some mechanism whereby the orientation can travel without the particles traveling. I don't know how to do that. So it's actually important to have particles. I don't know how. I mean, you need, if you write down a lattice model, you need to write down a lattice model in which this physics is present somehow. And of course, in reality, if you want this physics to be present, this is some kind of advection, some kind of carrying. Therefore, you need, let's make a comparison. Think of how orientation travels in the XY model, which is through these terms, versus this. You've been all told in, 9th standard or something, that heat travels by convection, conduction, convection, and radiation. This is conduction of orientation. This is convection of orientation. I don't have radiation of orientation unless you count the propagating waves as an example. I don't know. Okay. So you need to introduce this physics in a lattice model. Maybe you can do it. I don't know of any simple way of doing it. No, you can probably, meaning, look, after all, it's a PDE. And after all, if you're going to solve it on a computer, you're going to discretize it. You will be able to do it, but if you want to do it with a realization in terms of particles, you'll have to have particles that move a bit and then die. If you have particles that die as soon as they're born, you won't be able to. You need a mechanism for moving these particles from one side to the other. That you need. So I'll just tell you a kind of story of how long-range order comes in. It's interesting to see how it happens, and let's see if I'm able to convey it. Let's see if I can do this, okay? So let's say you've got a bunch of spins. You've got a bunch of these birds or whatever, spins or whatever you want to call them. This is actually an argument which is hard to find in the literature, but it's an argument due to Toner, but it can be found in an article by Francesco Ginelli. Everybody read that? So in case you aren't able to stay on board, you can look it up there. It's actually due to Toner in lecture notes that I can no longer find on the net. So what happened? How does an XY model disorder dynamically? What happens is, supposing locally this spin gets disturbed by some amount theta naught. And supposing the only dynamics you have is this. Then what will happen is that little error will spread diffusively, right? So delta, basically this thing will get shared among a bunch of spins. So after a time t, y t to the d over 2, the distance explored is square root of time, the volume is that guy to the d, right? Okay. So that's, and then we will eventually see from this that that process by itself will disorder the system in 2 dimensions. I'll come to that. So the number of such errors is proportional to time, right? There's some mean rate of making errors. Okay, each spin. So the RMS angle error, see if I can get this right. And you know, these errors are going to be plus theta naught minus theta, some amount like that, right? So the RMS angle error is going to be of order square root of r to the d times t, where r is t to the half. So let's write this as, or let's write t as r squared. So per spin, that's going to be, this is r to the 2 plus d over 2 divided by r to the d, which is r to the 1 minus d over 2, which is, if you want, you can do it in terms of t. Well, strictly, this of course actually doesn't tell you why you lose order in d equals 2. It tells you why you lose order in d even a little bit less than 2. But trust me, it's a growing log in d equals 2. Okay? So this is what would happen if you weren't helped. This is what would happen if you had this noise and this dynamics. So now we're going to try to save ourselves from this fate, because we know that in flocking systems, something else is happening. I guess I can go out. I can use this board, right? I've never reached this power before. Until, this is not good, this is okay. Yes. Which one? First one, yeah. So I'm saying that, you know, there's a mean rate of random kicks to the spin. Let's say each spin, your system is at some non-zero noise level or non-zero temperature or whatever you want to call it. Each spin gets some little kick. Let's call that kick some amount theta naught. It's some fixed number, but it's happening at a fixed rate. Okay, so that means in a time t, it'll happen t times that rate, that number of times. So it'll of order t. Okay. But the point is that spin, orientation is being distributed in 2 different ways. One is this diffusive spreading, but the spins themselves are wandering. A way of looking at it is the following. Supposing you've got a region where everybody's moving along, and supposing somebody makes a mistake. If somebody makes a mistake, they will either, if they slow down or speed up, they will get left behind or go ahead. And if they turn laterally, they'll leave that region. So the fact that the orientation is also a velocity actually makes regions of a flock kind of self-purifying. Because if somebody deviates from the true path, they're left. And the question is, does this dominate or does the diffusive spreading of errors dominate? Okay? Does the expulsion of deviants dominate or does the diffusive spreading of errors dominate? So let's try to calculate the this effect. Now, basically, lateral wandering finally it turns out is what saves you, and let's see why. Okay? So, it's there'll be now we're talking about the movement of these guys, not just the change in direction. Delta V transverse times time, which and what is delta? Remember, we argued that the transverse fluctuations of the orientation are just proportional to the angle, right? I drew that cartoon, which is probably still there. Oh, I've changed notation, delta S, yeah. I told the delta S perpendicular is of order theta, right? So the lateral wandering is of order delta theta RMS times time. And this delta theta RMS is what we just estimated here. Which is and the diffusive spreading. So remember, the particles themselves diffuse. Okay, so diffuse spreading of the angle goes as t to the half. You compare this with t to the half. So you have versus 1/2. What do you get? Let's see. Yeah. This dominates for d less than 4. Okay, so we're comparing spreading by lateral wandering to spreading by ordinary diffusion. Okay, so now let's take this idea and apply it specifically in d equals 2. Let me draw. How am I doing for time? Okay, I'll be okay. So what happens is if I imagine I take a region of a flock, after a time t, it will have spread in the following way. It will have grown to some width, which I'll call w perpendicular of time, which is of order the lateral wandering bit, and it will have grown to a width that way of order t to the half. Okay? This is w perpendicular. And let's see if we can so the number of spins is this times this. So we're now in d equals 2. The RMS error per spin will be this guy, which is the number of spins, times t. Because in a time t, each spin will make on the order t errors. Is t. The RMS error per spin is this guy times t. Let's do this right. Just a minute. Why am I doing it this way? Oh, yeah, it's important. Okay. So this many guys, that many errors, the angular error is the square root, because each error could be either way. And so this guy per spin is this divided by the area. Okay, you have to go through this slowly. So you have this many guys, each is making a small error. Over a time t, there's t of those errors, but each of the errors could be this way or that way. So the accumulated angle error is the square root of that. And per spin, it's that divided by the number of spins, which is this guy. And that, I guess, is, Let's see, 3 halves. We get a t to the quarter, w perp to the minus half. Yeah. Okay. Excuse me. Okay. Now, yes. We're trying to estimate the errors per spin, and ultimately what we're trying to do is to see, okay, let me just say at the end of it. Ultimately, we're trying to estimate whether W perp, whether delta theta grows like it did. Okay, where is it gone? Do I have it here? Yeah. If it is just plain xy, this in 2 dimensions actually was t to the 0, which is in fact a log. We're going to try to see if we can somehow get an argument using the fact of lateral wandering in this ordered phase to see if you can get the dominant effect at long times is a t to the minus something. Okay. So we've already seen that it's the lateral wandering rather than diffusive spread that dominates. So we're now going to calculate, we need to calculate W perp. So let's see. Where am I? Yeah. Right. So I have a t to the quarter, but W perp is also delta theta times time. That's what we argued earlier, which goes as t to the 1/4. So now we're going to equate these two. Let's do this carefully. So this is delta theta, is this guy, but it's also delta theta times t, right? So we just calculate delta theta here. So matching these two ideas together, we get a self-consistent expression for W perp, which is W perp to the 3 halves is t to the 3/4. Am I right? Do I really get that? 5/4. Excuse me. Good. Okay, and that means W perp goes as whatever this is, t to the 5/6. Yeah, 5/6. And therefore, delta theta, which we can now write in terms of W perp, goes as t to the minus 1/6. So what we've done is, by a somewhat difficult argument, but without ever really doing a field theory, shown that the lateral wandering of spins cleans up flux. So basically, there are multiple ways of looking at it. One is that S dot grad S means that whatever was happening here gets carried elsewhere. So if there's a local disturbance, that gets carried elsewhere. I don't know, there's many different ways of seeing it. I've tried to illustrate one of them without, and the thing to note is that it's precisely that nonlinearity, precisely the fact that the orientation is a velocity that is leading to this effect. I can't do more than this. I mean, if somebody asked me a question like happened earlier today in someone else's lecture, someone asked a question yesterday, I think. Finally, one has to just repeat the argument. All I'll be able to do is repeat this argument to you. What you can do is chew on the argument, look up Ginelli's notes where it's spelled out in letters that won't disappear by erasure, and see if you internalize it. However, the other thing we'll do is a couple of lectures from now, probably next lecture, I'll do a field theoretic treatment in which I ignore the density altogether, but keep track of advection, keep track of the S term. It turns out in 2 dimensions, 2 miracles happen. One is that you end up getting a kind of Galilean invariance restored, and you end up getting a kind of noise non-normalization condition. So 2 miracles come in, they give you, As a result, you get two conditions on two exponents, the spatial scaling and the temporal scaling. And it's enough to solve the problem. Enough in particular to give you long-range order. So what would long-range order amount to? Long-range order would amount to somehow, once again, calculating the angle correlation function and finding that this guy goes as 1 over q, not to the power 2, but to the 2 minus eta. If this goes as 2 minus eta, then the argument that made the angle variance grow logarithmically in 2 dimensions will no longer happen. Because integral d2q over q to a power smaller than 2 doesn't have the infrared divergence anymore. So we'll do that, but we'll do that. I mean, as I said, this argument wasn't simple to follow. You had to internalize a lot of things. Sit and read it. Let me spend the last 17 and a half minutes on something different. So if you look at my outline, okay, so that's it. I've somehow tried to convince you that long-range order in 2D flocks happens. So now let me go to a very different problem. You know, if you look at my outline, I said several things. I said that we're going to look at different dynamical regimes. One is flocking in a fluid versus flocking without a fluid. I talked about wet and dry active matter. The other is I talked about different types of order. Okay. So if I remember right, again, let me try to stick to the terminology that I used in my earlier notes. Yeah, I had wildly ambitious outline here, but anyway. Of the various topics I mentioned in my outline for actually the first lecture, let me pick one. Other kinds of order. I didn't call it that, I called it, I think this is probably the term I used, apolar order. See, the thing is, if we're interested in ordered phases, in condensed matter physics, there are all kinds of ordered phases. The first ordered systems that you encounter are the first systems you're taught in solid state physics, namely solids. We won't do solids today. Solids is an interesting subject. Another very abundantly found kind of condensed matter system is liquid crystals. And if you like, what we've been doing is discussing one kind of liquid crystal, namely a liquid crystal in which things are not only aligned, but they actually have a head and a tail which are different. And the alignment respects that difference and has something with a polarity. So the toner 2 system can be called polar flocks. However, actually, the most familiar liquid crystals, the ones that you use in your phone screen, computer screen, everything, are apolar liquid crystals. They consist of objects that have an axis, but are condensed into a state where that axis, either these are particles which don't have any head-tail difference, or these are particles which maybe they have a head-tail difference, but some of them are pointing one way, some of them are pointing another way. Okay. In fact, many liquid crystal forming molecules are actually of that type. They probably have some structural polarity, but under conditions of packing, they pack in a way that more or less cancels that polarity locally. In fact, you know, you can kind of imagine if you didn't, it's going to be problematic. Supposing you want to make a macroscopic, truly polar liquid crystal, and you want to make it out of molecules whose head is fat and tail is skinny or something, then the whole system will splay macroscopically. Right? Suppose you take a bunch of carrots and try to pack them. Fat heads in front, tail, pointy ends behind. You'll have to create some modulated structure. You'll have to create a little local wedge like this here and there and make something that's macroscopically modulated, not just aligned. If you just want alignment, it's difficult to do it with polar things. So apolar order is actually very natural. If you just take a bunch of cylinders, a bunch of ellipsoids, and pack them, this is what you get. And one of the first theories of entropic ordering was Gonzagal's theory of the phase transition in ellipsoidal systems. So let's understand this system. Now, you may find it peculiar to think about apolar order for an active system, because when you say active, you think of things that are motile. You know, if you've got a fish swimming, apolar fish are not going to get anywhere. Okay. It turns out, however, in living systems, many cells are elongated, and in many phases of their existence, actually are elongated but don't have a front back difference. Okay, and many cell aggregates, many non-migrating layers of tissue and things have this kind of structure. Now, if I take my particles of this system and assign to each one, I take each one and arbitrarily pick a head on each one and assign a unit vector n alpha to each. This is particle number alpha, and I assign a unit vector n alpha. Then if I take some coarse-graining region like this, and all these guys are pointing with heads somewhere one way, heads and tails kind of randomly placed, then the local average of n alpha, which would be the order parameter in the toner 2 or VCheck sense, will be 0. However, there is something happening. They are aligned. It's just that this is a bad way of measuring it. What you do instead is to ask, if I take two of them, I'm not taking the dot product, I'm just placing them side by side. So this is a second rank tensor. I can ask for the degree to which this average differs from what the value it will have in the isotropic case. So well, I'm just, this is my coarse-graining cell. So I'm going to write a continuum theory. So I'll draw a coarse-graining cell. And in fact, this, if you like, is macroscopic. I take everybody in my system. How do you calculate an order parameter? To begin with, you write down a macroscopic order parameter. You take all the members of the system, and this is the same guy, not different guys, alpha, alpha. That is n alpha I, n alpha j. So it's, right? It's called the nematic order parameter. So alpha labels the particle and I and j label directions, let's say. If you calculate this average, you can calculate completely globally, averaging over all particles alpha, or you could do it locally in some coarse-graining cells centered around some point R. Okay? No, it's a tensor. It's a second rank tensor. Here it is. That's why I put the components to show you that. So this is called the nematic order parameter tensor. And if you do it, imagine you've got a big system and you do it region by region locally. Because you're writing on a continuum theory, of course, you have to have some coarse-graining scale. And you do it on that coarse-graining scale and construct this object. And so now, supposing you have a system like this, and let's take a very simple case. Let's say you make a nematic liquid crystalline phase, and it's on some solid surface, so momentum conservation is not an issue. You don't have to worry, therefore, about conserved variables except for the number of particles. You want to make a theory of this guy and the number density. So you'd like to write down dynamical equations for the coupled dynamics of Q and rho. By the way, you understand, it's quite clear, right? You know that if these guys were pointing every which way at random, average Ni Nj would be 1 over d times delta Aj in d dimensions. D is the space dimension. Those of you who have ever heard of NMR will recognize that this is something like cosine squared theta minus 1/3. The same thing. Okay? And so what we want to do is to make a theory of a system of this sort. Now, I won't be able to do that in the time remaining to me, but what I can do is the following. There's several things you want to ask yourself. You say, look, this is a system of particles that's on average lined up, but doesn't know forward from back or left from right. So it's not going anywhere. Why is it active? What's so active about it? Well, of course, we are kind of now old and wise. We know that active really only means detail balance broken at the level of all the degrees of freedom. So we can guess that even though it's not going anywhere on average, might be something funny happening in it. Something funny in some interesting consequence of broken detail balance. And yes, yeah. So that's a good question. You could imagine states of this sort arising in a situation where the individual particles are motile, or you could imagine detail balance broken in a weaker way. Okay, so let me actually avoid that question and just say, maybe they're motile, maybe they're not, but even if they're motile, let's say they turn around very quickly, they backtrack very quickly or something. Okay. Then there is some confusion in many people's minds, including my own, about whether a weird phase is possible in which you have precisely half plus some sub-Poissonian number going one way and half plus sub-Poissonian number going the other way. You could imagine more exotic things. You could imagine, two interpenetrating polar ordered phases. I don't think that can survive any little bit of population exchange between the two, but I don't want to bet my life on it in case if I miss something. So at the moment, think of these particles as, they sort of go one way for a while and then they go the other way. So two things happen. Each particle is like this. It sort of moves back and forth a lot. And it also does some rotational diffusion. So you've got a rod. Normally, if you have rod-like molecules in a liquid or a solution, they do rotational diffusion. Okay? Translationally, they don't particularly move any more persistently than any other molecule. Even if they have a polarity, they don't start moving in one direction because then we could solve the energy crisis. Okay? They only do that if they're powered. So if you just had a bunch of rods in a fluid at thermal equilibrium, no matter how polar they are, they'll move around. Their centers of mass will execute diffusion. Their orientation will execute diffusion. The temperature, the kinetic energy in rotation and translation will be nicely equipartitioned. All those rules are off here. So if you were writing down a theory of these systems, there are many ways you could do it. You could write down kind of full-on kinetic theory, keep track of all the positions and all the momenta, both linear and angular, and put in, let us say, a different temperature in the angular and the linear. More than that, you've got a rod, right? So you could put in more kinetic energy for going this way than for going that way. You could make many kinds of two-temperature models. I won't do any of that. I'll do something very, very simple, which is I'll just say, what kind of equation of motion can I'll come to microscopic models in a later lecture. Right now, in the remaining 6 minutes, 20 something, let me just tell you, I want to write down an equation for the density, and I want to write down an equation for the Q tensor. If these were ordinary diffusing Brownian particles at thermal equilibrium, I'd get some kind of diffusion equation. And maybe I'd get a slightly fancier diffusion equation of the following kind. And I could get an anisotropic diffusivity. After all, I've got a system which has some local anisotropy, where this Dij is anisotropic because anisotropy may be proportional to Qij or something. So the idea is the following. We've got a system like this. It's a big system. Locally, there's some amount of orientational order here. If there is some amount of orientational order here, diffusion is going to be anisotropic to that degree. But that's not active. That's just anisotropic diffusion. Every anisotropic molecule has an anisotropic diffusivity, and this doesn't buy you anything interesting. So my claim is that if I'm being completely general and phenomenological, I will write down an equation of motion in which I'll write down whatever is allowed. Remember, I've identified my slow variables. I'm keeping track of Qij because I'm interested in the case where this system condenses into a pneumatically, this is called a pneumatic liquid crystal, into a pneumatically ordered phase. And I'll write down whatever is allowed. Density is conserved, so I've got to write down this as the divergence of some current. That current can have some ordinary diffusion. That's one piece. It can have something else. You make space here. Plus, I don't know, other weird things. This we understand. Components, excuse me. This we understand is anisotropic diffusion. This we understand is ordinary center of mass diffusion without respecting anisotropy. This is weird. It's perfectly allowed by all the symmetries of the system. It's a perfectly tensorial term. And what this term says is that if locally I have a spatial variation in the orientation, I have a current. And what this means is that if, so by the way, I didn't tell you how to write the QIJs in terms of angles. Imagine a state where these things are reasonably well oriented so you can assign an angle field to it. So then this will have components. So imagine I've got a system which is on average pointing like this, and there's some local variations in 2 dimensions which I characterize by the angular deviation from the mean aligning direction. Then this thing will be some magnitude times let's do this in 2 dimensions only. Just looking at this, by the way, you can see that by construction, it's traceless. Right? If you dot this guy into itself, it's 1. If you trace that, that's d, divided by d is 1. That's a traceless object. It's symmetric. So is this. So you're always allowed to write something like this in this form, with some magnitude in this guy. And the reason you get these 2 thetas is if you turn any of these guys by pi, you've gone back to the same configuration. They don't have a head-tail distinction. So, using that notation, let's say this is the xx, xy, yx, and yy component. This term is approximately, this term is going to give you an x component of the current proportional to the y derivative of the angle, and a y component of the current proportional to the x derivative of the angle. And no, it's not a curl in general. The picture is the following. What this term is telling you is that even though the globally aligned state has no polarity, if you perturb your system, so that's, the aligned state is everybody's pointing the same way, and that doesn't know which way to go. But if you now introduce a perturbation like this, curvature, this object has a polarity. It knows the difference between that way and this way. Likewise, if you introduce a spatial variation like this, this is called bend, this is called splay. Both of these have a polarity. Let's say I choose the polarity always to point in the pointed direction. So what this says is, anytime you have a curvature like this, you should have a velocity. Okay, and that is going to have as big an effect here as the fact that the orientation itself was a velocity in the Toner 2 model. Not obvious, but because you might, it said this gives you a term with 2 derivatives in this equation. Right? So the point basically, what I think I'm almost done. What this says is that there is potential for okay, first of all, if you make an ordered phase of these rods, supposing you forget about activity and stuff, ask for a liquid crystal. The angle fluctuations in a liquid crystal are big. And they're big for the same reason the angle fluctuations in the XY model or the Heisenberg model are big. The question is, can those angle fluctuations infect the density? And the answer is, through this term, it turns out they can. Basically, in a linearized theory, you're going to get, through this bit, terms of order plus other stuff. Okay. Now you might think there's 2 derivatives there, whereas in the Toner 2 model, if you remember, there was 1 gradient. You might think it should be a much weaker effect. Turns out it's not, and the reason is, it turns out the effect of the density back on the angle field is very weak here. And so this is enough to give you very big density fluctuations. So this, I'll stop here, and we can discuss more. So I would say that, again, as an exercise, figure out, show that this is the case, and show that this amounts to this. Just, don't worry about where this came from. I gave you a plausibility argument. Basically, the general argument is, if you have a system, if you have an active system, a system homogeneously driven out of equilibrium, if there is a vectorial asymmetry, there should be a current corresponding to that asymmetry. This is called the Curie principle. By some people from Curie. Actually, not just people from Curie, it's actually in literature. So we'll see next time that this has very dramatic consequences. So here's a system which is not moving. It's not a flock in that sense, but its orientation and mass current are coupled in a very dramatic way. And we'll look at the statistical consequences of that. Not necessarily. So one of my later lectures is called Scalar Active Matter. So I think it's sort of historical, you could have, I remember my student Aditi's PhD thesis, we were writing down, we were saying, okay, if I've just got a bunch of a number conserving system, maybe it's got two components or maybe it's anisotropic, what is the minimal, what diagnostic would I hit it with to tell if it's in equilibrium or out of equilibrium? Obviously you do some fluctuation, some correlation response kind of thing, okay? But we were sort of trying to ask, what is the minimal homogeneously out of equilibrium system without special orientational order, etc. And we were playing with that, but we went off that topic and went on to these topics because we were very interested in. Partly it's just, upbringing. I was interested in liquid crystals. Partly the game started with Toner and 2 and VCheck and flocks. So orientational order was very much in people's minds. But little by little, people have moved towards persistently, you need to spoil detail balance in some way. So one very simple way of spoiling detail balance is to have particles that keep moving in a given direction for a while, not ordering. But the simple fact that they're moving in a given direction for a while means that even though their damping is local, their noise is colored, that's already a breaking of detail balance. That's an example. So you imagine you've got a bunch of spherical particles, but on each one an arrow is drawn. That arrow tells which way it goes, and that arrow executes rotational Brownian motion itself. But if the arrow is pointing that way, it moves that way. That turns out to already be enough to do very dramatic things. You get phase separation, you get condensation without attraction. Basically, if you've got things following their nose, then if that nose takes a lot of time to rotate randomly, there's a good chance they'll come up against each other. Having come up against each other, they'll end up getting stuck. Like stupid, basically like they don't have the sense to turn around. And this is very important because many bacteria that function in crowded situations have a switch that if they run up against a wall, they reverse their flagellar motion. So if they don't, they'll undergo motility-induced phase separation. So I'm saying it's an effect that even exists in nature in some sense. So yeah, you don't have to have orientational order. You can have much more minimal kinds of consequences of being active. Yes, people are doing that. I would say that maybe those field theories are in better shape than ours in the following sense that, understanding phase separation in those field theories is in better shape than understanding phase separation in active systems with orientation order. So a decent amount of progress has been made by, there's lots of references. I don't want to say any name for fear that I forget any name. But several groups, Edinburgh, Syracuse, Cambridge, many people are doing this. So it's a very alive field, lots of things going on. And many of them, in fact, don't worry about spatial symmetry breaking at all. Many of them are, you can just plain condensation. So you all have lots of homework to do, yes? Yeah, yes. Persistent random walk, but you need something to get them trapped. If they're point-like persistent random walkers, they'll never get stuck. But if they're hard sphere persistent random walkers, then if the persistence, roughly speaking, you can think of a cluster and think of stuff coming into it at a rate given by the concentration of the bulk times their speed, and stuff escaping at a rate given by the rotational diffusion rate. And if the one overwhelms the other, you get condensation. So that kind of thing is there. Yeah, point particles, you just can't do it. Yeah, any size. So it's actually condensation by repulsion, which is quite funny. And there are. So one of the things I hadn't really planned to do is to show you guys any movies of real phenomena of these things. Some of those movies are from research in which some of us have been involved. I mean, there's real flocking in non-living systems, real condensation or trapping in. So maybe during the tutorials, I'll trot out some of those things also. So because, this stuff, we're as serious about the experiments in these systems as about the theory. We're not just doing it for the sake of doing theory.